So up till now, we've been dealing with static fluids, so fluids that aren't flowing anywhere. And we've been treating them ideally. We just haven't had to emphasize it quite as much. Now, when we want to talk about how fluid flows, we do need to come back and be a little bit more explicit about what we mean when we talk about an ideal fluid. So this isn't any different than when we started talking about springs, we talked about an ideal spring. When we get to the point in the semester where we start talking about gases, we'll start by talking about an ideal gas. And in each of those scenarios, what we mean is we're talking about the simplest model we can use that gives us effective answers. So for the spring, the ideal spring was one that didn't lose energy as it bounced back and forth. We didn't have to worry about the mass of the spring, and we didn't have to worry about the spring losing energy as objects bounced on. An ideal gas, again, is going to be a very special model that simplifies things so that when we think about a gas, it simplifies how we calculate things out. So our ideal fluid's the same idea. It's a model that we're going to use to describe a fluid that is valid for a lot of scenarios. Now there are plenty of scenarios where these assumptions that we're going to build in to an ideal fluid start to break down, and then this model won't work anymore. But for what we will deal with, the assumptions for an ideal fluid will be perfectly valid. So what are the properties that make up an ideal fluid? Well, the first one is the ideal fluid is incompressible. That means that when you squeeze the fluid, it doesn't compress, right? If it takes up this much volume, it's going to continue to take up this much volume, even as you try and squeeze it to take up a smaller volume, which means there's a constant density across the fluid. So when we go to describe the fluid using a density term, we only need a single term because the fluid's homogeneous in terms of its density. Second assumption, the flow of an ideal fluid is laminar. And so laminar is just a fancy way of saying that that flow is steady. The word that you're probably used to hearing for when something is not a laminar flow is turbulent. So we're going to assume that our ideal fluids are not turbulent. They don't have eddies and spirals and things like that going on as they flow. They simply are a stream that continues to flow forward and doesn't have any turbulent properties as it flows. Third assumption is that an ideal fluid is non-viscous, and the viscosity of a fluid relates to how layers flow past each other. And what we're going to assume is that there's no friction between those layers. So the more viscous a fluid is, the more friction there is between the layers of the fluid as you think about one streamline flowing past the next. Again, for an ideal fluid, we're going to take that friction property, that viscosity, and we're going to ignore it. So the last assumption that we're going to build in is that our ideal fluid is irrotational. And again, we're not going to focus too much on this one, but mostly what it means is that we're not going to worry about spinning within our fluid. These are properties that make up an ideal fluid. So let's think about how a fluid actually flows down some tube. So here we have a tube. Notice it's got a unique shape. So it's got a constant radius. So it's a cylinder with a constant radius down here, and then it expands to be a cylinder with a constant larger radius down on this end. We're going to let fluid enter the pipe over here on the left. We're going to let fluid leave the pipe over here on the right. The volume of fluid that passes by a given location during some period of time is known as the volume flow rate. And the letter we're going to give for the volume flow rate is big Q. So we can define Q as thinking about some chunk of volume that goes past in some amount of time. And so again, if we want to think about that in differential terms, that just means that we have dV over dt, where again capital V here is the volume that's flowing past. Again, that volume I can think of, and it's easy to see within these nice cylinders, is it's some area times some distance in the x direction that's flown by. And so that area in this case happens to be constant. I can pull that out, and so that leaves me with dx dt, which I know is the definition of the velocity. So Q, my volume flow rate, is going to be equal to what's the area of that pipe times the velocity at which the fluid is flowing past. So if we think about what's going on with our pipe here, we've set up our pipe so that there are no sources or sinks, meaning that there's no additional way for fluid to enter the pipe. That's a source. There's no way for fluid to leave the pipe other than how we've designated at the end of the ends of the pipe on the left and the right. What that means is that we're not adding fluid, we're not letting fluid leave, so the fluid that enters the pipe on the left-hand side has got to be the same as the fluid that leaves the pipe on the right. And then, of course, because we have an ideal fluid that's flowing through our pipe, that fluid is incompressible. Incompressible means that I can't squeeze it, so that tells me that the same amount of fluid has to flow past any point along the pipe in the same time interval. What this means is pick any 2 points and Q has to be the same. So if Q is the same at any 2 points, that means this product of the area of the pipe times the speed at which it's flowing past, A times V, that's always constant as my ideal fluid flows through my pipe. This equation, A1V1 times A2V2, the idea that that product AV is always constant, is known as the continuity equation. And you've seen this, you've experienced this numerous times where you think about water flowing out of a garden hose. And then if you wanted that water to come out faster, you took your thumb and basically put it over the end of the water hose. So what you were doing was you were making the area that the water was able to leave the hose, you were making that smaller. And so by making the area smaller, that meant that the velocity the water was coming out had to go faster, which sure enough, instead of just flowing out of the hose in a nice easy way, now it's spraying out of the hose and traveling a much farther distance. So this is the entire function behind a nozzle. So what that nozzle does is it basically gives you a way to make the area that the fluid has to flow through smaller, which means that the volume the fluid's flowing has to increase, and so that nozzle gives you the ability to send fluids at high speeds even though they don't need to be traveling at high speeds the entire way through the pipe.